video here on more polar stuff for calculus. This is day 2 of polar. We're really focusing on area bounded by the polar curve for this one. So there's a couple area formulas. Well, really just one area formula you have to know here. So pretty much this is the formula you got to know right here. Is the area of a polar curve is 1/2 from the two angle measures r squared, which is the radius, d theta. So that's how we find these out. The trickiest part within these is really the bounds, because that can sometimes throw us for a little bit of a loop as we go through. So what's important to know is we have to know how to sketch these. If we don't know how to sketch them, we're not going to know if it's going to repeat itself, because it's totally possible that some of these graphs will repeat themselves and just keep doing the same thing over and over again, which we don't want to double count the area. So sketching it is a huge deal for this lesson here. So, well, why is the area this? We can just throw this out of left field. If you remember back in pre-calculus, when you found the area of a sector, by the way, just a portion of the of a circle, was 1/2 r squared theta. Okay, this is pretty much the exact same thing. If you look over here, it's 1/2 r squared d theta. So it's kind of sort of where it comes from. There's a more technical way, but I'm going to kind of show that off to another time. If you ask me to, I will happily do it. But for this video, this is the area form that we need to know, and let's just kind of go on from there. Okay, so first example here is going to sketch this graph and find the area bounded by the graph. Okay, so again, we're focusing on sketching. This one's not a bad one to sketch. So to sketch this, again, my suggestion is to always sketch in Cartesian coordinates for something that we should be used to. So this is 2 plus 2 sine theta, so nothing weird going on here. So the period is unchanged, so we're going to go all the way to 2 pi. Okay, so here's pi over 2, and here's 3 pi over 2. And we're shifting this up 2 with an amplitude of 2, so we're going to go up 4 and then down to 0. And this is sine. It's going to start right here, and it's going to do this different color, actually. Start here, and then we're going to go up, middle, down, middle. And I'll kind of just draw my sinusoidal axes right here. It's not really there, that little dotted green, but that's just kind of giving you an idea of the shape of this. And there we go. And this is going to help me graph this bad boy right here. So really, at 0, I'm at 0. Sorry, at 0, I'm at 2. I will eventually be it over there. So at 0, I'm at 2. At pi over 2, I'm at 4. 1, 2, 3, 4. At pi, I'm out 2. So in this direction, I'm out 2. At 3 pi over 2, I am at 0. And then at pi over 2, I come back over here. So I have to start here, there, then there. So it looks like this. If you notice, it's increasing. Okay, and then we're going to start to have a smaller radius in this part to get to 0, and then a smaller radius here. And that's how you graph that one. So we really want to find the area of this. So the whole reason that it's important to go ahead and sketch this is to know my bounds. Well, I sketched it all the way from 0 to 2 pi before I started to repeat, because I could keep going and I would just get the exact same shape over and over again. So super important there is I have my bounds. So my area for this is 1/2 from 0 to 2 pi r squared, which is going to be 2 plus 2 sine theta all squared d theta. Okay. Sometimes these are calculator, sometimes they're not. This is calculator, then we pretty much just type this in. Let's treat this as a non-calculator because we just need to get used to this. So we need to expand this because there's nothing we can do otherwise. So a equals 1/2 0 to 2 pi. If I were to expand this and distribute, I would get 4 plus 4 sine theta plus, I think I would get 8 actually. I'm lying, 8. Because I'd get 4 sine theta plus 4 sine theta, which is 8 sine theta plus 4 sine squared theta. And this is all d theta. I'm just double checking my work here. Okay, we're good. So I can integrate the 4, not a big deal. I can integrate the 8 sine, not a big deal. This sine squared, I cannot integrate that. So I'm going to have to use one of my handy dandy formulas that I learned way back in unit 7. So 4 plus 8 sine theta, and to remind you, sine squared theta is equal to 1 minus cosine 2 theta all over 2. Okay? So I'm going to take this sine squared and replace it with that right there. So what's going to be nice here is that 4 is going to cancel out that 2, left with just 2 of these. 2, 1 minus cosine 2 theta d theta. And then just do a little bit more combining here before I do any integration. Make this look a little bit nicer. 0 to 2 pi. This is going to be 4 plus 8 sine theta plus 2 minus 2 cosine 2 theta d theta. So I'm going to combine these twos to give me a 6. I'm actually going to distribute that 1/2 all the way through as well, because it makes everything kind of nice here. So I'm going to distribute that 1/2 all the way through. So it's 4 plus 2 is 6, divided by 2 is 3, plus 4 sine theta minus cosine 2 theta. All right, and then from here, I'm pretty much good to go with antiderivatives. So I'm going to get 3 theta. This will turn into a minus 4 cosine theta, because the antiderivative of sine is negative cosine. And then this is going to be minus, this is going to be end up being a 1/2 sine 2 theta. Evaluate that from 0 to 2 pi. So to do that, I'm going to get 3 times 2 pi minus 4 times cosine of 2 pi minus 1/2 sine of 2 times 2 pi is 4 pi. Get that lovely answer there. And then minus, plug in the 0 now, so 3 times 0 minus 4 cosine of 0 minus 1/2 sine of 2 times 0 is 0. And then I'll kind of save you all the work here. You can go ahead and simplify everything out. Some things are nice, cancel out. Some things be zeros. I'm going to end up with 6 pi here. So I'll let you do the algebra on your own, but you should end up with 6 pi here. Okay, so the problem isn't too bad. It's just a lot of simplifying until we get down to here. So it's not too bad. Again, you have to know how to sketch this so you know what your bounds are. And we're about to do 2 examples where the sketching really will lead us to figure out that it's not always going to be from 0 to 2 pi. Okay? So here we go. Sketch and set up the integral of the expression to find the area of one petal, which means that we're going to have petals here, of r equals 2 sine 3 theta, and do not evaluate. So we're just setting this one up. Pretty typical. It's just a setup only for these problems here. Okay, so to sketch this, I need to go ahead and sketch this guy right here. Now, we usually go from 0 to 2 pi, but our period here is going to give me a 3. So what I'm going to do here is, this is going to end up, by the way, the period, just in case you forgot, is always going to be 2 pi over b. And 3 is the b value here. So in this case, our period is going to be 2 pi over 3. So I'm going to go from 0 all the way to 2 pi over 3. And now I'm going to do all my markings here. So I got 2 pi over 3. So halfway would be pi over 3. Halfway from that would be pi over 6. In between those two right there would be, oh boy, 5 pi, just checking, should be pi over 2. All right, so I'm going to go ahead and start to sketch this. If this is sine with an altitude of 2, so I'm going to go up 2, I'm going to go down 2. So we're actually going to be dealing with negatives here. So this is sine, so it's going to look like this. Here, 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 and here. Okay? So this is going to be this graph right here. Now, I'm sketching a rose here, and I'm going to tell you just from experience, this is not enough of my graph. Okay? I have 3 petals because of the period is 3. I'm going to have 3 petals. Okay, this right here, this positive represents 1 petal. This negative right here represents another petal. I actually need to go just 1 more petal further. Again, this is just coming from experience of doing this. So if I go a whole nother petal further, if I add pi over 6 to each of these, I'm going to end up with, hold up. I'm going to end up with 5 pi over 6. If I add another pi over 6 to that, I'm going to end up with a pi. So you can kind of see what's going on here. And then, boom, this is going to give me my 3 petals. So I have a petal up here, petal down there, petal right there. So now let's go ahead and sketch this out. So at 0, I'm at 0. At pi over 6, which is like over here-ish, I'm going to be out 2. So put that probably right about here. And then at pi over 3, which is right along this line right here, I'm back at 0. So what does that look like? It looks like this. So that's 1 petal right there. And then at pi over 2, I'm at negative 2. Right? So when this is the pi over 2 direction, I'm actually going to end up down here because it's negative 2. Okay? So, and then at 2 pi over 3, which is along this line right here, I'm going to end up at 0. So it's going to look like this. Okay? This is not proportion because I'm not the best drawer in the world. Just deal with it. And then we're going to end up doing the same thing here. We're going to end up going out to 5 pi over 6, which is going to be somewhere over here, and it's going to be there-ish. And there you go. And then after that, it would just keep repeating. So if you wanted to find the area of the entire thing, you would integrate from 0 to pi. Okay? Actually, I wouldn't do it that way. I'll tell you how I do it in a second. But we're just trying to find 1 petal. So 1 petal is actually this area right here. All right, so we're going to have to integrate this now. So my setup to find my area is 1/2. For this petal, I'm starting at 0, and I'm ending at pi over 3. Okay, that's very important, ending at pi over 3. And then that's going to be r squared. It's 2 sine of 3 theta all squared d theta. And that's my setup. And I'll find us the area of 1 petal. If you needed to find the area of the entire rows, all you would do is find the area of 1 petal and then multiply it by however many petals it has. Okay? Second example is like the exact same example. Just this one uses cosine. So cosine, it's not as obvious when you do the sketch to see where 1 petal is. So the setup of it is a little bit different, but it's going to be the same idea here. So we're going to go ahead and sketch this out. This is a rose with, it looks like it has 2 petals. Actually, it does not. It has 4 petals. I'll explain why. Cosine's a little different. And it really helps when you sketch it. That's really what I'm trying to get at, is you need to really sketch it to figure out how many petals this has. Cosine's a little bit on the weirder side with this one. So for cosine 2 theta, again, my period would be 2 pi all over 2. So my period is pi. So I'm going to go out to pi. So halfway is pi over 2, pi over 4, 3 pi over 4, and I'm kind of just trying to fit that in there. 4 down 4. Okay, so what you're going to do here is sketches. This is cosine, so I'm going to start up. So here's my sinusoidal line, by the way, is on this axis. So you're going to start up and then down. Here, here, here. So it looks like this. Okay, so your 1 petal is actually from here to here. Okay, so I can actually set this up before I do anything else, and then I'll finish the sketch. So to set this up, the area would be 1/2. And our petal, if you notice, because this isn't a full petal right here. My petal's from pi over 4 all the way to 3 pi over 4 of my radius, 4 cosine of 2 theta d theta. And make sure you square that radius. So there you go. All right, so if I were to sketch this, this is actually not enough of a sketch, because I'm going to start here at 0. I'm out at 4. And then out at pi over 4, which is this line right here, I'm at 0. So it's going to look like this. Okay? And then at pi over 2, I'm at -4. So remember, this is the direction. So I'm at -4, which is down here. 1, 2, 3, 4. And it's going to be the same thing like this. So you do it like this, you can kind of start to figure out how many petals we're going to have. At 3 pi over 4, which is this line right here, we're at 0. So it looks like that. And then at pi, I'm out at 4, which looks like this. So this is not the full graph. As you can see, we actually we need to connect. So I need to keep going. So I'm going to keep going on this graph right here. And then all of the pi over 4s in between. So this would be 5 pi over 4, and this one would be 7 pi over 4. No, I know I am squeezing it in there. So figure out how many petals something has. Graphing is just a huge way of figuring it out. So if we're going to end up going like this. All right, it's supposed to be a nice clean. There's supposed to be no intersection right there. It's supposed to be nice and clean. So this ends up having 4 petals. And to find the area of 1 petal, this is your setup right there. Okay, so again, the easiest way I do it is I just do the rectangular graph, and I just find just a point from 0 to 0, and I just go ahead and find the area between those petals. You could do this with different bounds from like 3 pi over 4 to 5 pi over 4. You could pick any of those petals. It does not matter. All right, and that's going to wrap up our video here on polar.